Okay, so we're gonna continue. So the gamma distribution is has this form. So alpha c the PDF is x alpha minus 1 e minus beta x, right? So the form, if alpha is 1, the form is something like this. If alpha, well, so the shape changes with this parameter, and also the larger the is more skewed. Okay, you can read this document, R code, if you're interested. So I'm going to move on to these properties. The first property is additivity, something called additivity. So sum of the gamma distribution is gamma if the scale parameter is the same. So the first property and the shape parameter just added, right? So the MGF of y is e to the ETY, and then this one is, because y is a summation, so product of ET xi, and then by independence is something like this, and then use the gamma distribution, the property of gamma distribution in 1 minus beta t, alpha minus alpha I, something like that. So that is minus summation alpha I is a MGF of gamma beta distribution, right? So that gives the proof. Second part is MGF y equals cx, the same story. So second part is the scale. If you multiply constant, then only the scale parameter changes. So et cx, right? So then you can tc, you can do change of variable to et es x, and then that is 1 minus beta s minus alpha, that's positive, and then you can write it as c beta t minus alpha ct, positive, right? So this is MGF of gamma alpha c beta, something like that. So that gives the proof. So a special case is alpha equal to 1, then then in the PDF, beta alpha x alpha minus 1 e minus beta x, right? So alpha equal 1, then this one becomes 1, and so everything should be nice and looks nice. So we have only exponential form, and that is called exponential distribution. So the variance is the square of the mean, because the mean is alpha beta and variance is alpha beta square for the gamma distribution. Chi-square, okay, and chi-square distribution is another special case of gamma distribution. This is the form because with beta equal 2. So beta equal 2, then the, okay. So actually we should put, so this is not correct. We should put some domain, right? I mean support, specify the support. And R is parameter, positive, and this is degree of freedom. So the mean is, mean of chi-square distribution is the degree of freedom R, and variance is 2R. So one, but we recall that we have we already chi-square 1, right? So we already show that. So 1 and MGF of chi-square distribution is 1 minus beta. Beta is 2, right? 2t minus r over 2 for 1 minus 2t is positive. So this is a special case because this is gamma ri over 2, right? And so the summation of this guy should be gamma of the summation ri over 2, which is chi-square, distribution. So that we already proved this additivity for gamma distribution. So we have only to prove it for so it's just chi-square distribution is just a special case. Now this is also important result for normal distribution with a positive definite covariance matrix. Then we can actually create a transformation, back transformation, right? So if you you can obtain this one, and that is actually normal distribution with mean mean 0 and variance I. So that is standard n-dimensional standard normal distribution. So this one is essentially z prime z, right? So that is essentially I equal to 1 to n zi square, where zi is normal 0, 1. So because of the additivity, each one is chi-square 1. So the summation of this and then zi is independent, right? So zi is independent, so zi squares are also independent, and so that implies that this one follows chi-square distribution with degree of freedom n because of the of this corollary. Okay. So that present. So this is for beta.